यार अपना माइक जरा जोर से बोलना। ओके
He has started recording.
ओके
सभी लोग
Morning, children.
Morning, sir. Good morning, sir.
Good morning, sir.
Good morning, sir. Good
गुड
morning,
मॉर्निंग
sir.
सर।
Okay, I.
गुड मॉर्निंग सर।
Morning. Okay, we will start. We will continue with whatever we stopped in the last class. That is like ammonia. Okay. So in the last class, I had told you about the properties of ammonia. So I had told you that ammonia is highly soluble in water. Okay, so I also said that the experiment to prove that thing is nothing but the fountain experiment, which we had already done with hydrogen chloride. So we will use the same method again. Okay, so I will show you the video for the fountain experiment of ammonia. So this video includes the preparation of ammonia as well. So that will be like, little interesting for you, and it will be like, from the beginning how they can you stop the annotation? I'll stop the class right away. Okay, and this is the first and the last warning I am giving to each and every one of you. If I find any scribbling on the screen, that's the end of the class. Okay, and then you look for some other chemistry teacher. Okay, yeah, so you better stop it. So I will share you the video. So in this video you will see how ammonia is prepared, collected in the round bottom flask, and then how the setup is arranged, and how finally you get to see the fountain arrangement. Okay, fountain experiment. So please pay attention. Okay.
The flask is filled with highly soluble alkaline ammonia gas. It dissolves in water, causing a reduction in pressure that draws more water into the flask. The demonstration is tricky, but the result worthwhile. The fountain takes place in this apparatus, a 2 decimeter cubed flask fitted with a bung with a piece of glass tubing with a jet at one end, similar to the end of a pipette, and a syringe attached to a short length of flexible tubing. The tip of the jet should end up about 2/3 of the way up the flask. This flask, and indeed all the other apparatus, must be absolutely dry. If necessary, rinse it with propanone and allow it to evaporate. The ammonia is generated in this apparatus. 880 ammonia is heated in here with a couple of boiling stones. As it passes through here, there's some potassium hydroxide in there which will dry it, passes through here and is collected by downward displacement of air because the ammonia is lighter than air. Heat the ammonia solution gently for several minutes. When you think that the flask is full, test the bottom with damp indicator paper, which will go purple, showing that the flask is full. When you're confident that the flask is full of ammonia, stopper it. The flask can now be left for some time, and you may prefer to prepare the flask of ammonia and perhaps a spare before the demonstration. Have ready a 2 decimeter cubed trough full of water and add to it some universal indicator. And you want enough to give a clearly visible colour far more than you'd use for a titration, for example. Add to it some acid, and you want just enough to make the water turn red. Then you need a stand and a clamp or a ring to hold the ammonia. Quickly, so that no ammonia escapes, you need to remove the bung and replace it with the jet assembly. Keeping the rubber end of the tubing in the water. Squirt some water from the syringe into the flask, and this may be enough to start the fountain. If nothing happens immediately, then swirl the flask, keeping the rubber end of the tubing in the water. As the water emerges, it turns from red to purple due to the alkaline nature of the ammonia. The fountain will continue for some time until all the ammonia in the flask has been displaced by water. Should the fountain fail to start, the most likely reasons are either the apparatus being wet or leaks in the apparatus. This apparatus does have a small leak, but it has still worked, but it is probably the
Okay, I hope you understood how the experiment works, right? Okay, so this is the best explanation you can get for the fountain experiment and the experiment itself. Okay, so the same can be applied for HCl. As I said already, like the solution which we are taking in the trough, that is at the bottom, the only change will be the color of that thing because of the kind of litmus solution which we are using. So for HCl, we'll be using blue litmus solution, which enters a flask and turns red due to the acidic nature. And in case of ammonia, we'll be using red litmus solution in the trough, which enters a flask and it becomes blue in color. Okay, so it depends on whichever indicator you're taking in the flask, the color change depends on it. Our textbooks mention litmus solution, so we'll stick to the litmus solution color. So if they are using other indicators, the color obviously will change. Okay, so this was the experimental proof of ammonia being highly soluble in water. So again, the question which will be asked from fountain experiment will be like, what do you infer? What is the inference of fountain experiment, or what do you understand from fountain experiment? These 2 points have to be written for sure in that case. That is, ammonia is highly soluble in water and ammonia is basic in nature. Okay. So moving on to the next topic, the second method of preparation of ammonia is from metallic nitrides. Okay, metallic nitrides are nitrides of metals, and here we are studying only two, which is like magnesium nitride and aluminium nitride. Okay, in your textbook you have got three reactions: magnesium nitride, aluminium nitride, and calcium nitride. But then we are not studying calcium nitride because it is not mentioned in your scope of syllabus, right? So we will study only these two reactions. The process and everything remains the same except for the ions which are being swapped. So like if I'm taking magnesium nitride, the product form will be magnesium hydroxide. If I'm taking aluminium nitride, the product form will be aluminium hydroxide. That's the only change which we observe. So obviously if you're using calcium nitride, you'll be getting calcium hydroxide over there. Okay, the setup is almost the same. The only thing is like we are not using a round bottom flask over here because we are adding a liquid reactant over here, unlike the other preparation where you use both the solid reactants, that is ammonium chloride and calcium hydroxide. So here we are taking a conical flask, and in the conical flask we are taking magnesium nitride in it, and through a thistle funnel we are adding warm water. Now, whenever this question is asked, like how do you prepare ammonia from metallic nitrites, it is very important for you to write that the water taken in this reaction is warm. Okay, because this reaction does not happen with cold water. Okay, so even if you are being asked to write an equation, the equation should be mentioning that the water taken is warm, right? So we are adding warm water through the thistle funnel, and a reaction happens over there, and ammonia gas is formed in this conical flask, which moves through this delivery tube, and it gets collected in this drying tower. As we had observed in the last experiment, same thing. The drying tower contains a drying agent which is quicklime, that is calcium oxide. It dries the ammonia gas, deprives it of any moisture present in it, and it sends dry ammonia over here, which rises through this tube and gets collected in the gas jar. Again, method of collection remains the same. Ammonia, being less denser than air or lighter than air, starts filling up over here, that is at the top, and slowly gets filling up in this gas jar, gradually displacing the air in a downward motion. So that is why we say that it is collected by downward displacement of air. Okay, so that's a quite simple experiment. And now the question, the other type of question will be this one, the statement which is written in the end, that is why ammonia is not prepared by this method. The reason is being the metallic nitrides, that is metallic nitrides are quite expensive. So the process of making the nitride is also expensive, and that is the reason why we never use this method. We always stick to cheap methods for preparation. Okay, so that's the reason why we don't use this method of preparation for ammonia. Okay, so here magnesium nitride is reacting with water, and it forms magnesium hydroxide plus ammonia. Similarly, aluminium nitride will react with water and will form aluminium hydroxide and ammonia. So you can remember the general reaction over here, which would be like metallic nitride plus water will give you metallic hydroxide plus ammonia gas. Okay, so this is how you prepare ammonia from metallic nitrides. Okay, is there any doubt in this question? Okay, I got two hands raised. Okay, yes, Tanisha.
Uh, Sir, if there's warm water in that flask, the chisel funnel won't the air that is the ammonia that's been created, won't it go up the chisel funnel? Won't there
See,
be a
it will be like,
possibility?
see, whenever we are using a thistle funnel, see, we have an option of like, taking enough of the reactant so that the reactant, whichever we are pouring into the conical flask, gets filled up till the tip of the thistle funnel. So don't go by what is the level of water which is present over there. Okay, just understand that whenever we are using this water on this, you'll just make sure that it is filled till this tip so that no gas escapes through this. So that will be taken care of. So that need not be explained everywhere because it is understood. Okay.
Okay. Thank you.
Okay. Yeah. Yes, Arthak, what's your doubt?
Sir, this diagram can come in the exam for labeling and for information.
Labeling will come. Yes. Yes. Okay.
Okay.
Yeah.
Yes. Thank you, sir.
Yeah. Yes, Adiba, what's your doubt?
So, can you explain why we have used a conical flask here?
So we can use any type of flask, my dear. The only thing is they have chosen to take a conical flask. You can take any apparatus which can, like, undergo this process. The only thing
Okay,
I told
sir.
you is that we are not just keeping it in the inclined position as in the first one, because in this case we have to add a liquid reagent, so it has to be kept upright. So they just chose a conical flask. That's it.
Okay,
Okay.
sir. Thank you.
You're welcome. Yeah. Okay, I hope that's it. There are no other doubts in this. So we will move on to the next topic. Okay, so that is, okay, Advait. Okay.
Sir, in that quick lime section, such as nothing below that flash, so wouldn't the quick lime fall down?
See, don't go by that. Okay, so it's like, it's a representation, Advait. Okay, so you just need to know, if you remember the other diagram which I had shown you for the laboratory preparation of ammonia, the drying tower will be manufactured in such a way that it can hold calcium oxide.
Okay.
Okay, so so you don't worry, like that will not fall down. So they will be keeping some kind of a, like, like a stand or something like that. Okay, so which will like hold it. Okay, So
Okay.
it will be kept in a good position, so you don't worry that that will not fall down. Okay, you just have to understand that CaO will be present over there in the middle of the drying tower, so that it separates the ammonia gas which is having moisture and the one which is not having moisture. Okay. Okay, so due to some reason, I can see that this meeting is going to end in 10 minutes. So even though it ends in 10 minutes, I'll like reconnect. You all stay connected on this thing, okay? I don't know what is happening this every time. Next time, I guess I'll put a new link so that, you know, this type of trouble does not happen. Okay, so that's it. So we will move on to the next topic. Okay, so the next topic is manufacture of ammonia by Haber's process. Now, this Haber's process you have heard from like grade 7. Although we have not gone into detail about this, is actually a very important process which you have to understand. Okay, so Haber's process is the process which we use for producing ammonia in bulk quantities. Okay, so here we are using nitrogen gas and hydrogen gas, okay, and 1:3 ratio, and we are producing ammonia. Okay, this reaction is a reversible reaction. As you can see, there is a reversible arrow, and it is also an exothermic reaction. So obviously, like, you know, initial heating would, like, you know, suffice for the continuation of this reaction. Okay, so in this part of the chapter in Haber's process, you just have to understand the equation. You need to know the condition. So when they ask you to write the reaction, like what happens in Haber's process, write the reaction of manufacturing ammonia by Haber's process, you have to write this reaction, and you will include all the conditions, that is the first four. Okay, these things. Okay, so that would be the temperature that has to be maintained. The temperature is 450 to 500 degrees Celsius. Then the pressure will be 200 to 900 atmosphere. The catalyst will be finely divided iron, and the promoter will be molybdenum. Okay, so these things, this question will come as a 1 mark question or a 2 mark question. Depending on the weightage of the question, you will answer it. Okay, so it's not required, like, you know, if the question comes under, say just like coming under balancing equation in section 1. So in that case, you just have to make sure that you are putting the reversible arrow and the delta sign, and you can put a catalyst. Okay, so temperature, pressure, even if it is not mentioned, is fine. But then if this question comes in section B for more than 1 marks, so they will, like, you know, expect you to write all these conditions. So like the question may come for 2 marks. Okay, so like 1 mark will be given for writing the equation properly, another 1 mark will be given for writing the conditions. Okay, so just to keep you informed that we don't have a system of, like, you know, giving half mark anywhere in the question paper. So you have to understand that even if you make a single mistake, even everything else is, like, you know, the same or correct, you will still lose your marks. Okay, so you have to make sure that you are writing everything properly. Okay, so that you get full marks over here. So you have to write these things. So the only thing which you have to understand in Haber's process is that the equation, that is N2 plus 3H2 giving you 2NH3 plus delta. Delta is for heat, and plus delta means it is an exothermic reaction. The temperature is 450 to 500. Pressure is 200 to 900 atmosphere. Catalyst is finely divided iron. Finely divided iron is like iron powder. Okay, iron powder, very fine powder of iron. And promoter uses molybdenum. This reaction is reversible and it is exothermic in nature. Okay, this is all you have to understand from Haber's process. There is a lot of things mentioned in the textbook under Haber's process. You don't have to study any of that except for the last part, which will be like this ammonia which is formed over here is like this reaction being an exothermic reaction. There might be a possibility that this will undergo decomposition and form the reactants again, that would be like, you know, nitrogen and hydrogen. So to prevent that, we have two methods of collection of ammonia. Okay, so as in every method, like, you know, even if it is laboratory preparation, there is a specific method which we use for collection of ammonia. So you have to make sure that that particular thing is like, you know, that particular thing is taken care of. So in this process, that is Haber's process, there are two methods to collect the gas or separate the gas from the reactant, exactly, because this might get mixed with this reaction. So as I'm telling you again, this is a reversible reaction, so there are chances that the reactants are not completely, like, you know, getting converted into ammonia. So there might be a possibility that they might get mixed up. So in this, like, you know, process, the container or the, like an apparatus in which this particular reaction is happening, it might be possible that it will contain all the three gases, that is N2H2 and NH3, right? So to prevent the mixing of this, I mean to separate this ammonia effectively from nitrogen and ammonia, sorry, hydrogen, we have got two methods. The first method is called as liquefaction. Uh, Liquefaction is a method in which, like, we are taking this ammonia gas and we are applying pressure at low temperature and converting it into its liquid state. We have studied the term liquefaction in our lower grades. So it is nothing but conversion of a gas into its liquid state, right? So we are taking this ammonia, the mixture of ammonia, nitrogen and hydrogen, wherever this thing is held in. What we do is we apply pressure into that container wherever these gases are being, like, stored, and we decrease the temperature. So what happens is that ammonia is actually a very easily liquefiable gas. So it gets into its liquid state quite easily. Meanwhile, N2 and H2, that is nitrogen and hydrogen, they cannot be converted into its liquid state very easily. Liquid nitrogen and liquid hydrogen and all are possible, but then the kind of pressure which has to be applied and the temperature to be given is, like, quite different from whatever is required for ammonia. So as a result, what happens is that when we just apply pressure and decrease the temperature, we can easily convert this ammonia gas into its liquid state. Meanwhile, the nitrogen and hydrogen gases remain in their gaseous state. So thereby we can, like, easily separate the ammonia gas from these, like, this mixture of nitrogen and hydrogen. The second method is by dissolving in water. We have already studied previously, like, ammonia is highly soluble in water. So what we do is we take this mixture of gas, that is ammonia, nitrogen and hydrogen, mixture of these three gases, and we pass that mixture into water. Okay, so when we put that mixture into water, ammonia being highly soluble in water gets dissolved quite quickly. Meanwhile, nitrogen and hydrogen are almost insoluble in water. This we have studied in the chapter hydrogen. We have studied, like, how hydrogen is not soluble in water and all, right? So the rate of solubility of nitrogen and hydrogen is actually quite less, as a result of which we can easily separate ammonia. So these are the two methods. So if in the exam they are asking you a question like, how do you separate ammonia from the reactants in Haber's process, you can write any of these two processes. Okay, if it is a 1 mark question, you can write either liquefaction, or you can write dissolving in water, or you can write both, because it doesn't take much time to write both of these things. Okay, so even if you write one of the methods, you will still get the marks. Okay, I hope this is clear. Is there any doubts? Is there any doubts in this? Can you please ask or raise your hand, or, like, put a message? Okay, okay. Why do we take finely divided ion as catalyst? Because we have already studied that when we increase the surface area, the reactivity increases. So instead of taking a piece of iron, if I'm taking very fine powder of iron, I guess, like, it will increase the effectiveness of the catalyst. That is why we are taking finely divided iron. Okay, then who else? Okay, Sahil. Yeah, Sahil, what's your doubt?
So can you explain liquefaction again?
Liquefaction, see, liquefaction, there is a process in which we are taking a gas and we are applying pressure and reducing the temperature and converting it into a liquid. So we can, like, take any gases which are liquefiable, and we can convert that gas into a liquid by applying high pressure and low temperature. This process is called as liquefaction. Okay.
Thank you, sir.
You're welcome. Yes, Vaishnavi.
I did not get the dissolving in water wala thing.
Okay. Okay, the video, I mean, the session is going to end in a minute. If it gets cancelled, just stay. Okay, as I told you already. Okay. So the dissolving in water is nothing but, like, we take the mixture of gases. We have the mixture of gases in a container. We pass this mixture of gases through water. So ammonia being highly soluble, that's the only gas which dissolves in water. The other two gases remains undissolved. So we can easily separate the ammonia, which is, like, present in water, and the other two gases which do not dissolve. This is just about dissolving in water. It's quite a simple process. Is that clear? Vaishnavi?
Yes, sir. Yes, sir.
Yeah?
Samjha.
Okay.